For this insulation thermal resistance problem, your TA Indiana is going to be perched back on his hamster wheel. Any type of cylinder problem, he knows his cue is back there on his cylinder to provide you guys with some moral support. Parts 1 and 2 are going to be a quickly easy setup, and then part 3 is the actual problem here where we're going to set up an electrical circuit and show you how to calculate electrical resistance for conduction, convection for both walls and cylinders. And we're going to ignore surface contact resistance, but I'll talk about it a little bit just in case you need to include it for another homework problem or a test. So the drawing on the screen is actually set up for part 3 since it already has the insulation applied. For part 1, we're looking at just the pipe itself. So just like the water in the middle and the gray outside, right? That gray ring is the pipe. And so if the temperature on the outside wall of the pipe is already known, 150 degrees, and the ambient temperature is also known, then this is just the easiest possible convection problem. And if I grab the main easy convection equation from my FE exam reference manual, that's heat transfer equals HA delta T, where delta T is the surface temperature minus the ambient temperature, and H is the heat transfer coefficient, then really I just need to solve for the area of the pipe that's touching the exposed air. So this is the surface area of a cylinder, and the surface area of a cylinder is just going to be the perimeter of a circle times the length of that cylinder. So later in this course, when you actually study convection, you will look back at this problem very fondly because convection problems can get way more complicated than this. Right, this is only the easiest possible case, but again, we're studying conduction right now. This is just like the setup to the main conduction part of the problem. Now, it is okay to leave your temperatures in Celsius when you're doing subtraction. If you're ever multiplying or dividing by a single temperature, you do need to be in Kelvin, but a difference in temperature can be Celsius because if you added 273 to both temperatures, it would just cancel itself out anyway. So it is okay to do a delta T in terms of Celsius temperature. All right, so plug everything in, 42.4 kilowatts, and that's the amount of heat being lost from this pipe to the ambient air. All right, so for part 2, we've got a weird unit here, 52 cents per therm. So this is going to be a big unit conversion setup. All right, so I'm starting with kilowatts, which is kilojoules per second. I want to find annual cost. So first I'm going to convert seconds to years. So 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. And even though I'm recording this video in 2024, let's pretend it's still 2023 because 2024 is a leap year, which is 366 days. Okay, so next we were given the conversion, therms to kilojoules, which is good because therm is not a unit you're going to use very often. There's no reason for you to memorize this. If it's not given, this is something you'll just have to look up. You're not expected to remember how many kilojoules in a therm. All right, then multiply by 52 cents per therm. And from that, we get about $6,500 per year. But we were also given in the problem that our heater is only 75% efficient. So even though our system is emitting $6,500 of heat into the atmosphere, we're actually using more than that amount because it's only 75% efficient. So we have to divide our dollars by 0.75 to get it the larger number, right? So about $8,800 is how much essentially our electricity bill or our gas bill is. So we're spending $8,800 to get this heat, of which $6,500 of it is emitted to the atmosphere, and the other 25% is wasted, which means it's also probably getting emitted to the atmosphere as well, just not from the surface of the pipe. All right, and thank goodness your TA Indy arrived because now we're about to start part 3. That's the actual conduction thermal resistance problem, so you're just in time. All right, so we start to set up this problem for real, given, find, concept, assumption, solution. So for concept, this is going to be a thermal resistance problem. Usually any type of conduction or convection problem where you have heat flow through multiple sections in series, like it goes through the pipe and then through the insulation and then into the atmosphere, right? Whenever you have this and then, that's a good time when you're going to want to use thermal resistance because you have all of these heat transfers in series with each other. And ultimately, the thing we're trying to find is lowercase t, the thickness of the insulation. All right, so your TA Indy hopped back on his treadmill to represent all of the insulation, right? The round cylindrical insulation we're going to be adding to the pipe for this problem. What a smart TA we have. All right, so first I'm just gonna write down the total electrical circuit, basically every sort of heat transfer that's happening all the way from the center water in the middle, all the way to the atmosphere on the outside. So on the inside, we've got the temperature of the water, and then there would be convection from the water to the inside of the pipe. And that convection term is a resistor. Then inside the pipe from Ti to To, that is conduction inside the pipe, another resistor. Now where the pipe touches the insulation, that's actual physical contact. I'm gonna add an extra resistor there, call it surface resistance. Because the outer surface of the pipe is not necessarily the same temperature as the inside of the insulation. Because there's not perfect contact between the two, there's actually like tiny little gaps in between them. We can model that surface contact as an extra resistor. It's usually going to be ignored. Most problems you'll ignore surface contact, but I'm still going to write it there for completion just in case. Okay, then if I call T1 to T2 the temperature at the inside and outside of the insulation, I can get another conduction resistor for heat through the insulation. And then the very last resistor is going to be from T2, the outside of the insulation, to T infinity, that's just like the air temperature. And that's going to be a convection term. And so this is a one-dimensional circuit for one-dimensional conduction when you have all of your heat transfer going in one direction. The water to the inside of the pipe, to the outside of the pipe, to the inside of the insulation, to the outside of the insulation, to the atmosphere. And each one of those temperatures of interest has a resistor in between it. And that resistor represents either conduction or convection that's happening. When actually solving this type of circuit problem, we can actually ignore parts on the inside because we're given the temperature on the outside of the pipe, that 150 degrees. So this means we don't care about the water temperature or the inside of the pipe. The circuit analogy, temperatures are like voltages. Okay, so why resistors at all? What's the similarity? So think back to electrical circuits, Ohm's law. V equals I times R. So in circuits, current is the thing that actually moves. So in heat transfer, that's going to be Q, that's heat. And in electrical circuits, current moves from high voltage to low voltage. Voltage is like a potential. In heat transfer, temperature is your potential. Temperature is your voltage. Heat goes from higher temperature to lower temperature. And so in electrical circuits, the thing that resists, the thing that tries to slow down how much current goes is a resistor. In heat transfer, everything else in the equation is going to be your R. There's going to be lengths and areas and K and H. I'll rearrange that as I equals V divided by R. So then in heat transfer terms, we've got Q is equal to delta T divided by everything else. So for convection, we've got this HA term. And so since the R is in the denominator, the resistance for regular convection is 1 divided by HA. For regular conduction through a wall, the equation is Q equals Ka delta T over L, the Ka over L. But since resistor is in the denominator of Ohm's law when set up this way, the resistance to heat transfer through a wall will be L divided by Ka. Now in this problem, our wall is not a regular rectangular wall. Our walls are cylinders, they're round. And what this means is that essentially the problem is sort of two-dimensional. Imagine that you take your cylinder and you like unwrap it and straighten it out. It wouldn't be a rectangle, it'd actually be sort of a trapezoid. So the resistance due to conduction through a cylinder has a slightly different equation than through a regular wall because you have to account for this inner and outer radius. And not something you really need to memorize, but just something you can grab from the FE reference manual, from your textbook. This is a really common equation, you'll kind of find it everywhere. And so what we're gonna do now that we've set up this heat transfer problem as a circuit, we're essentially the reason to do this is so that we can combine all of these different convection and conduction terms into one single resistance that captures all of them. So in our problem, we're given 150 degrees on the outside of the metal pipe and 15 degrees as the atmospheric, like the room temperature. So these are our voltages, and we're interested in heat transfer between them, which is like the current flowing between those two voltages, heat transfer between those two temperatures. And to do that, we just need the combined resistance between those two temperatures. This lets us completely ignore the entire inner part of the problem, the inner surface of the metal pipe, and also the water on the inside. We don't care about them because we already have temperature on the outside of the pipe. We only care about the resistances between the two temperatures that we know. And so, just like I can write V equals I times R, or I equals V divided by R, I can write Q dot is equal to delta T divided by the total resistance. And for all of these resistors in a series, that's the easiest possible case. I can just add them all up. So the amount of heat transfer is the 42,400 watts that we calculated earlier, but multiplied by 0.1, because that's the whole point of this problem, is we want the insulation to reduce heat transfer by 90%, meaning there will only be 10% left. Delta T is my two known temperatures, 150 minus 15. And again, it's okay to leave those in Celsius when doing delta T, but if you want to convert it to Kelvin to be safe, you can go ahead and do that. You'll get to the same 135 degree difference. So now looking at the three resistors, I'm going to make an assumption for this problem that surface contact resistance is 0. When in doubt, make that assumption. Whenever you have two solid surfaces in contact, if you don't have any information in the problem about contact resistance, then assume it's 0. 1, it makes the problem easier. And 2, it shows your professor that you understand, that you have a good understanding of thermal resistance and heat transfer in general by making good, relevant assumptions. It shows them that you understand the context or how problems could get more complicated. So now my R1 is going to be the resistance inside the insulation due to conduction, and this is going to be that natural log resistance. And then my R2 is going to be the resistance due to convection on the outside surface out to the air. And that's going to be 1 divided by HA from the regular basic convection equation. Now I'm solving for R2, and I can already tell by looking at this that this is going to be kind of problematic because I got R2 inside a natural log, inside a fraction, in the denominator of another fraction, and there's a different R2 somewhere else. It's basically impossible to combine a natural log and a polynomial. So there's probably no easy way to actually solve this algebraically to get an answer for R2. That means you're going to have to actually finish this problem numerically. And by making that determination now, that will stop me from getting frustrated from performing a lot of extra algebra that I don't need. So what I'm going to do to solve this numerically is just going to be to plot it. So in order to plot, I just want to get this function set up as something equals 0. And then when I plot the something, I'll just look for where it crosses the x-axis, and that'll be my answer for R2. So I think the easiest way to do this is going to be to take all the resistors and multiply those over to the other side, take the 4,200 and divide it, and then subtract the new fraction over. So we've got 3 fractions equals 0. And R2 is the only unknown, so when I plot it, I'm just going to plot R2 like x, basically. So I'm going to plot y equals natural log of this plus rx that plus the fraction equals 0. So if you got a graphing calculator, you could put it in that. I'm just going to type it into Desmos and pull the graph up here on the screen. And you see we get an answer 0.0692 for R2. And that's in meters because all of our units were in meters. So like 7 centimeters. All right, so we get an R2 value of 0.0692, and it's a good sign that we got a value bigger than 0.05 because that was the inner radius. So, if we had got an answer less than 0.05, we definitely would have messed up. And 0.07, right, is on that same order of magnitude. It's a little bit bigger than R1. So this is a pretty good sign that we're on the right track. Again, if we had gotten R2 of like 7 meters, obviously something would have gone wrong somewhere. So I look back, what was I even trying to find for this problem? And it was thickness, not outer radius. So the thickness of the insulation, right, is the difference between the outer and the inner radius. So subtract those two, I get 1.92 centimeters as the thickness of insulation that will reduce heat transfer by 90%. So if you think your TA Indy running on his hamster wheel helped us out a little bit with this problem, go ahead and hit the thumbs up to let him know you appreciate it. And if you want another thermal resistance example problem, click on the video shown on the screen here.